Okay, we're back for part two of our lecture on logic. And part two of the lecture here is going to be devoted pretty much to the implication compound statement and some of the issues surrounding that. It can be a little tricky to use, and so we'll spend some time kind of working out some of those issues. And then we will also use what we do to do a couple of proofs of things we've already seen before, actually, and talk about maybe a little bit of the strategy of doing a proof, of proving things. So we're going to be talking about the implication statement. So let's actually write down its truth table again. And so its truth table is this. Here's P, here's Q, and here's the statement we're interested in. P implies Q, and we have here, we have both true, we have true and false, we have false and true, and we have false and false. And so let's put this here. And so we know that the implication statement is true in each of these cases except the second one. So we have T, F, T, and T. So this statement is false only when the antecedent is true and the consequent is false. And I don't think I've actually pointed those terms out before. So let's actually do that here. Let's first say this is the consequent in an implication. And this is the antecedent of an implication. And so as I said, the implication is false only in the situation where, or only in the case where the antecedent is true and the consequent is false. And it's also very important to keep in mind that this is the same truth table as for the compound statement, not P or Q. As you can easily see, and when we did that last time, we did that in the first part of the lecture. And it's useful to be keeping that in mind because it can clarify things about the implication statement. Let's look at a few examples of statements that are implications and try to see some of the, as I said, some of the issues here having to do with when the implication compound statement is true and when it's false. So here, notice that when the implication P implies Q is true, that does not mean that the consequent Q is true because P is true. In fact, of course, it's possible that the consequent is actually false and the implication statement is true. If the antecedent was false as well, then Q here could be false and we would have an implication would be true. So the fact the implication is true doesn't mean necessarily that the consequent is itself true, and even when the consequent is true, it's not true in some sense because P is true. All this means is that not P is true or Q is true. That is, P is false, as in these two lines, or Q is true, as in these two lines. So any one of these three implications true. So let's look at a couple of three examples of statements that'll help bring this out a little bit. So here's the first example. Let's suppose that P is the statement, Barack Obama was born in the United States. Well, that's true. Of course, there was some controversy about this engendered by some people a few years ago and maybe even continued currently, but I think we can agree that indeed Barack Obama was born in the U.S. is a true statement. And let's suppose that Q is the statement, I was born in the U.S. That happens to be a true statement also. And so since both P and Q are true, the implication, P implies Q is true. That's the first line over here. In fact, let me number the lines here because I'm going to refer to line 1, line 2, and so on. And so, this implication, P implies Q is true in this case because Obama was born in the U.S., true. I was born in the U.S., true. So the implication is true. But now, let's change things around just a little bit. And suppose I say that P is Barack Obama was born in California. Well, in fact, Barack Obama was born in Hawaii. So he was born in the U.S., but he was not born in California. So that's false. Q, I was born in California. That happens to be true. So now I have P is false, Q is true. The implication is still true because that is line 3 in the truth table for our implication or our conditional compound statement. So that implication is true, but it's not the case that I was born in California because Obama wasn't born in California. And in the first case, it's not the case that I was born in the U.S. because Obama was born in the U.S. So the implication is not an argument. It's not some kind of reasoned out argument. It's simply a compound statement formed from two other statements. It's important to keep that in mind because it is easy to get confused, even from people who understand that and are confident in what they're doing. It can be easy to confuse oneself sometimes. The implication statement is not an argument. It's just a conditional statement. So let's take a third example in the same vein here. Let's suppose that R is the statement, I am Barack Obama. Well, that's false, okay? But now let's look at the implication in which we have the antecedent is P and Q. Barack Obama was born in the second case. Barack Obama was born in California, and I was born in California. That conjunction is false because while I was born in California is true, Obama was born in California is false. So the conjunction of the two is false. And of course, R, the consequent of the implication is also false because I'm not Barack Obama. But the implication is still true. Again, this is not an argument here as to why I am or am not Barack Obama. It's simply a compound of some other statements. So, of course, this last example is one where the antecedent itself is a compound statement, a conjunction, and the antecedent is false, and the consequent is false as well. So that corresponds to line 4. So actually, each one of these three examples here corresponds to a different line in the truth table. The first one, they're both true, that's line 1. The second one, the antecedent is false and the consequent is true, and so that's line 3. And the last one, the antecedent, the compound statement, is false and the consequence false. So the implication is again true. So I think that those examples there are a little bit helpful in seeing how the implication works, what the implication actually is, and perhaps more to the point for this example, what it isn't. It's not an argument. It's not the case that they were reasoning out that the consequent is true from the antecedent, or even that the consequent doesn't follow from the consequent doesn't follow from the antecedent. So that's a first set of examples for seeing how the implication compound statement works. So we often have a statement that is like this, that a universally quantified statement that for all x in some set S, some open statement is true for every one of the x's in here. Well, that's a closed statement. There are no free variables running around. This is an open statement, but this quantifies it, so that closes it so that the free variable is no longer free, it's been quantified. So we could also write this as for all x in S implies P of x is true. And maybe I should put in here that what we really mean when we write P of x, it's that P of x is a true statement for the particular x. So here I've just rewritten this, and I've written it so that it actually is an implication. And I've done that kind of intentionally. We don't typically take this and rewrite it like this, but what we often do is we write this as an implication and leave out the universal quantifier. So I would write this as x in S implies P of x. Now, both of these are closed statements. The x is quantified. This is clearly an open statement. So let's write that here. This is an open statement because it has the free variable x here that hasn't been quantified. And so this is not the same as these two, but we often write this when we mean one of these. These are both the same. When we mean this, we often leave out the quantification, the universal quantifier. And you could say, well, why do we do that? It seems like that might be a little bit loose, a little bit not exactly kosher. And in fact, Hammack, in his book of proof, he talks about exactly this. And he says something, and by the way, this is going to sound a little bit critical of Hammack and his book, but the book is actually wonderful. It is a terrific little book, absolutely. But this is one place where I think I would have done things just a little differently. He says that we often leave this out and just write this part here when we mean this, because having to always write this, we'd kind of get tired of always writing this. Well, I suppose that might be true, but that's not the main reason that we actually see this. We're going to see this in a few minutes in a proof, and in that proof, we're not writing this because we're tired of writing this or it's kind of too much trouble to write this. We write this because we have translated, or let's say we've transitioned. We've transitioned the proof from some kind of closed statement to using an open statement in a way that is workable. So that's probably a little obscure right now. We'll see it when we get to it. But I just want to point out that, in fact, there's a real reason for sometimes often in fact, leaving out the quantifier and turning a statement into an open statement. And we'll see that, we'll do it, and we'll see how it works. Okay, so now let's go over here and do a few examples of this. So let's start off with an example that is for every x in R, x squared is greater than or equal to 0. Well, the first thing to note, of course, is that that's true. Okay, so that's true. This is a closed statement, and that closed statement, the way I've written it is not an implication, but this closed statement is true. But notice that I could have written this closed statement this way. Notice that here I have for all x in R, for all x in S, so R is playing the role of S. And x squared greater than or equal to 0 is playing the role of p of x. That's an open statement. That's an open statement, but it's closed by quantifying this. And so this is a closed statement. It's true. But I might have written instead, I might have written it this way. And if I did that, I would have, instead, I would be writing x in R implies x squared is greater than or equal to 0. It's supposed to be x squared. And of course, that is an open statement. So it's not true or false in and of itself. It's true or false depending on which x we're talking about, right? So this happens to be a statement that is true for every x. Every x, if it's in R, then its square is greater than or equal to 0. So this, I would say, is true for any x. If it's in R, if it's a real number, its square is non-negative. Okay, let's do another one here. Let's say for every x in R, x squared is strictly positive. Well, of course, that is false. And so before writing any more down, let's just write this in this open statement style. And of course, that is an open statement. So it's not true or false. It is true or false depending on the value of x. So if x is 0, so this is f for x equals 0. And of course, if x is anything other than 0, then this is of course true for every real number. If x is anything other than 0, that would be true as well. And so this open statement would be true. But when x is 0, x is a real number, that's true. X squared is not positive, that's false. So in that particular case, this is false. And so this is not a true closed statement because it's not true that for every x in R, x squared is positive. So this, of course, is false. So let's say, and here I'm going to write the open statement first. So let's write x squared greater than 0 implies that the absolute value of x is greater than 0. And so that, you'll notice, is actually true for every x, but notice that it's true for every x in a different ways. So as long as x is not 0, that's true, and that's true. And I'm in line 1. But when x is 0, notice when x is 0, this is false, and this is false. So even when x is 0, the implication is true because I'm down here in line 4. And when x is not 0, the implication is true because I'm up here in line 1. So that means that this is true for every x. And so now I could go back and quantify this. For every x, let's say for every x in R here. So let's take this off here. Let's say for every x in R, so that is true. But notice again that it's true in different ways for different x's. Okay, so let's say x squared greater than or equal to 0 implies absolute value of x equals 0. That is, this is, let's say, if x is equal to 0, this is true, this is true. If x is not 0, this is true, this is false. So again, the truth value of this implication varies depending on the value of the variable x. And so here, if I put for every x in R, we have, this is false, because there is one x for which this is, sorry, there's lots of x's for which this is true, and this is false. So this closed statement is false, and now say x squared less than 0 implies that absolute value of x is greater than or equal to 0. That, of course, is for all x, this is false, and this is true. So this implication is true for every x. So let's put the quantifying universal quantifier in here. That is true from line 3 here for every single x. And then one last example here, and that will be that x squared less than 0 implies absolute value of x equals 0. And x unequal to 0, this is false, and this is false, and x equals 0, we have this is false, and this is true. This is line 4, so the implication is true. This is line 3, so the implication is true. So we know that for every x in R, this implication is true, the open statement is true, and therefore the closed quantified statement is true. And so I think these various examples, again, bring out the various things that can happen when we're working with the implication compound statement. The first point to make is that this is the same as not P or Q, and that it's false only when P is true and Q is false, so that even when Q is false, we could have the implication being true, as in line 4. And once we're working with open statements, if we're working with an open statement, that the truth values of that open statement, they will differ depending on the value of the variable or the variables in the open statement. So I think those examples are useful for kind of seeing how things work here. So now what we'll do, I think, is we'll take this off and we're going to return now to a couple of results that we obtained a little earlier in an earlier lecture. And we'll actually give proofs of those results, and we'll see how the proofs use the notion of implication. We'll see how the issues that we've developed here in the last few minutes will show up, and that'll give us some insight into some strategies, perhaps, for doing proofs. Okay, so let's take this off, and then we'll be back in just a moment.